Have you ever watched those stock tickers just fly across the screen and wondered, what is actually happening behind all of that? Well, I can tell you it's not magic, it's code. And today we're going to pull back the curtain on the two Python libraries that are, quite literally, the secret backbone of modern finance.
I mean, think about it. Every single second, the financial world unleashes this absolute tsunami of data. Stock prices, trading volumes, economic reports. It is a constant, deafening roar of information. So the real question is, how does anyone possibly make sense of it all? How do you find that one tiny signal in all that noise?
Well, that question right there brings us to the core problem we're talking about today, the financial data challenge. And it's a challenge of both size and speed, one that our old, traditional tools were just never built to handle.
Seriously, we're talking about millions upon millions of data points being generated every single minute. Now just try feeding that into a standard spreadsheet. It wouldn't just slow down. No, it would literally buckle under the pressure. It would freeze, crash, and just give up. The scale is just way too massive.
So to conquer this mountain of data, you really need two distinct superpowers. First, you need the raw, unadulterated processing power to perform millions of calculations in the blink of an eye. And second, you need the masterful ability to organize all that chaos, especially across the all-important dimension of time. And this, right here, is where our two heroes enter the story.
All right, first up is NumPy. And NumPy is all about one thing, and one thing only: pure, blistering speed. Think of it as the high-performance engine that does all the heavy mathematical lifting for Wall Street. It is the raw muscle.
So what's its secret weapon? Well, it's a concept called vectorization. And here's the key idea. Instead of processing numbers one by one by one, it handles entire arrays of them all at the same time. The reason it's so ridiculously fast is that under the hood, these operations aren't even running in Python. Nope, they're executing highly optimized, pre-compiled C code. It's a genius little trick.
And this really shows you the difference, right? A normal Python loop, that's like a cashier scanning every single item in your grocery cart, one by one. It is painfully slow. Vectorization, on the other hand, is like some futuristic scanner that zaps your entire cart and prices it instantly. That's the kind of speed we're talking about.
So what does this actually look like in practice? Well, imagine you need to calculate the risk of an investment portfolio. With NumPy, you just load the data, you define how your investments are mixed, and then, boom, it calculates the expected return and risk almost instantaneously. A massively complex task becomes simple and unbelievably fast.
Okay, but all that speed is pretty useless if your data is a total mess, right? You need a way to make sense of it before you can calculate anything. And this is where our second hero comes in. If NumPy is the engine, Pandas is the master organizer, the time master. Its specialty? Dealing with the single most critical dimension in finance: time. You see, Pandas takes raw, messy, chaotic data and transforms it into this beautiful, intuitive structure called a data frame. Just look at this. The dates are neatly organized, acting as an intelligent index, and each stock gets its own column. It's basically a spreadsheet on steroids, and it's perfectly built to handle data that changes over time.
And one of its most powerful features is something called the rolling window. This lets analysts look at data through a moving time frame, like, say, the last 30 days, and calculate things like a stock's volatility. This is absolutely crucial for understanding if an asset is getting more or less risky. It helps you see the hidden trends that a single data point would totally miss.
And it gets better. What if you want to zoom out from that daily view to see the monthly trend? With Pandas, that's just a single line of code. This ability to resample data to just effortlessly pivot between different time frames, well, it's essential for both short-term trading and long-term financial strategy.
Now, while each of these tools is an absolute powerhouse on its own, their true mind-blowing potential is only unleashed when they work together. This is where the modern financial toolkit really truly comes to life.
You see, they aren't just two separate tools that happen to play nice together. They are deeply integrated. As this quote from our source material says, Pandas is literally built on top of NumPy's foundation. This means they speak the exact same language. The brain and the brawn are designed from the ground up to work in perfect harmony. Think of it like a perfect relay race. Pandas takes the baton first, expertly organizing all the messy financial data into a clean, time-indexed data frame. Then, it hands that perfectly structured data off to NumPy's engine for those lightning-fast, vectorized calculations. It's organization meeting speed. And here's a super clear example of that. You can take a pandas data frame holding years of stock returns, and with just one command, multiply it by a NumPy array that represents your portfolio weights. And the result? You've just calculated your entire portfolio's historical performance in a fraction of a second. It's that powerful. So, what does all this incredible power and organization actually lead to? Let's take a look at how this dynamic duo of code translates directly into capital and shapes the entire financial industry.
Well, for starters, these tools are the engine behind algorithmic trading bots, the ones that can execute thousands of trades before a human can even blink. They power the complex risk management systems that protect banks from market crashes. They're used to optimize multi-billion-dollar portfolios for the best possible return. And they feed the clean, structured data that makes modern machine learning in finance even possible. This combination allows for some serious sophistication. Analysts can instantly calculate complex metrics like the Sharpe ratio, which in simple terms just tells you how much return you're getting for the amount of risk you're taking, or something like a stock's rolling beta, which shows you how a stock tends to move compared to the overall market. These aren't just abstract numbers, they are deep, actionable insights.
And honestly, this quote just says it all. NumPy and pandas aren't just helpful tools. They are the fundamental backbone. The entire world of quantitative finance, the data-driven computational side of Wall Street, it all runs on this code. So when you have the power to analyze the past with this level of speed and clarity,
All right, welcome. Today, we're going on a bit of a quest. We're diving headfirst into the chaotic world of financial markets to see if we can actually find some order in all that noise. We're going to follow the exact path a financial analyst takes to try and make sense of it all.
So let's just start with the biggest question there is, right? Can we really predict the market with data? I mean, it's the billion-dollar question. Today, we're going to break down how analysts even begin to tackle this. This is the heart of our entire quest.
Every quest needs a map. And for us, that map is something called a financial time series. Just think of it like the market's heartbeat, recorded at regular ticks of the clock. It's basically a running history. Stock prices, interest rates, you name it. And it's the very ground we'll be walking on.
Okay, our quest officially begins. And like any good adventure, the first thing you have to do is gather your supplies. We can't analyze anything until we have the raw materials. And that means collecting the data that's going to fuel this whole journey.
And analysts pull in a ton of different information. We're talking daily stock prices, what's happening with currency exchange rates, even big picture stuff like national interest rates. This data comes from everywhere. Sometimes it's simple files like a CSV, other times it's pulled directly from powerful APIs that plug right into sources like Yahoo Finance. But here's the first major reality check. The raw data, it is a mess. Seriously. It's almost always full of holes, errors, and weird timestamps. So the first real job of an analyst isn't some glamorous prediction, it's cleaning up the past. You have to turn that chaos into a clean, solid foundation before you can build anything on top of it. Okay, so once our data is clean and all organized, now the detective work can really start. This is the fun part, the exploratory phase, where we start digging around, looking for those hidden patterns and stories that are buried deep inside the numbers.
And the number one challenge here is something called separating the signal from the noise. So all those daily, jumpy, up and down movements in the market, for the most part, that's just noise. What we're really hunting for is the signal, that underlying long-term trend that shows us where things are actually heading.
And check this out. This shows you exactly what I mean. On the left, you've got that raw, jagged, volatile data. It's all over the place. But look to the right. By using a simple technique called a rolling average, we can smooth out all those crazy spikes. And all of a sudden, a much clearer picture of the trend emerges.
That moving average is one of the most fundamental tools an analyst has. By constantly taking the average over a specific window of time, say the last 50 days, it helps us see past all that daily chatter and get a real sense of the market's true momentum.
Now we are getting to the really cool part. Think of this next phase as the training montage of our quest. We're about to take our simple, clean data and forge it into something way, way more powerful.
This is such a great example of that transformation. On its own, a single data point like a daily stock price isn't all that helpful. But from that one number, we can engineer all these powerful new clues, or features. We can figure out the 7-day return, we can measure the volatility, we can even check if the data week matters. This gives our predictive models so much more to chew on.
And this process creates all the essential weapons in an analyst's arsenal. You've probably heard of some of these technical indicators. Moving averages, which we just saw, help spot trends. The RSI can give us a hint if a stock is maybe overbought or oversold. And Bollinger Bands are great for measuring volatility. Each one is like a different power-up for our quest.
But hold on. Before we can use any of this cool stuff to predict the future, our data needs to have a very specific property. It's a nerdy word, but it's crucial: stationarity. The simplest way to think about it is that most models are like runners who need a flat, predictable racetrack. They just can't work right if the ground keeps shifting up and down. They need that stability.
So how do we create that stable track? Well, luckily, analysts have a whole toolkit for this. They use techniques like differencing, where you look at the day-to-day change instead of the price itself. Or they use detrending, which mathematically removes the big upward or downward slope. These steps aren't optional. They're absolutely required to get our data ready for a model.
All right, the preparation is done, the data's clean, the features are forged, the time series is stable. We have finally reached the climax of our quest. It's time to use everything we've built to actually try and forecast the future.
And you know, this process isn't magic. It's a very structured workflow. First, you build a model. A common one is called ARIMA, which is built for this kind of data. Second, you use that model to make your forecast. And third, and this is so important, you do a reality check. You evaluate how good your forecast actually was compared to what really happened.
So how do we know if our crystal ball is working? With cold, hard numbers. We use these evaluation metrics to basically give our forecast a grade. They tell us, on average, how far off our predictions were from the real world. A lower score is better, and the whole game is to try and get those error numbers as low as you possibly can.
And of course, the journey doesn't just stop there. These same principles can take you on way more advanced adventures. You can analyze an entire portfolio of stocks at once. You can build models that specifically try to predict volatility itself. Or you can even go hunting for weird anomalies in the data. The possibilities are huge.
So, there we have it. We've completed the quest. We followed the analyst's path from a messy pile of raw data all the way to a financial forecast. But, you know, the real adventure is when you take this map and start charting your own course. Because really, the best way to get a feel for this isn't just watching, it's doing. It's applying these steps to a data set that you're curious about, whether it's stocks, crypto, whatever. That's how you really make this knowledge your own.
You know, this quote from Carly Fiorina just nails it. The whole quest of a financial analyst is about this exact transformation. You take raw, meaningless numbers, you turn them into useful information, and then you turn that information into actual, actionable insight.
So, I'll leave you with this final thought to chew on. This power of forecasting, it goes way beyond just the stock market. If you could build a perfect model to accurately predict just one thing in the future. All right, let's get right into it. If you've ever worked with data, and I mean really worked with it, you know that feeling, right? Staring at a loading bar, just waiting for a huge file to open. Well, today, we're talking about the solution to that exact headache. How PyArrow and Feather can basically create an express lane for your data workflow.
But before we get to the solution, let's just sit with the problem for a second. We've all been there. That painful, slow process of getting data out of a file and into your code so you can actually start working. It's this massive bottleneck, and honestly, it's been a thorn in the side of data folks for years. I mean, seriously, just think about it for a second. How many times have you run a script to read some big CSV, then walked away to make a cup of coffee, came back, and it's still chugging along? It's not just you, I promise. This is a totally universal experience, and it's a killer for both your productivity and your train of thought.
In this analogy, it's just perfect. Think about traditional formats like CSVs as old, winding country roads. Yeah, they'll get you to your destination eventually, but the ride is slow, it's bumpy, it's inefficient. PyArrow and Feather, though, they are the brand new 6-lane superhighways built specifically for data. They are designed for one thing and one thing only: pure, unadulterated speed.
So let's meet the architects behind this new data highway. The two technologies we're focusing on are Apache Arrow, that's the foundation, the bedrock, and the Feather file format, which is like the perfectly smooth pavement you'll be flying across.
So what in the world is Apache Arrow? You know, the best way to think about it is as a universal translator for your data. It sets up a standard way for data to be laid out in your computer's memory. So when you're moving data between, say, Python and R, there's no need for this long, costly conversion process.
everybody's speaking the same data language, and that just wipes out a huge bottleneck right there.
And that brings us to Feather. If Arrow is the language everyone agrees to speak, then Feather is like a perfectly written book in that language. It's built right on top of Arrow's tech, and it is hyper-focused on one single mission: to be the absolute, hands-down fastest way to save your data frame to a disk and read it right back. No frills, no fuss, just raw speed.
So what does all this get you in the real world? Well, first off, obviously, blazing fast performance. But then you get this really cool thing called zero-copy reads. This means your computer can access the data right where it is without having to make a whole new copy of it in memory. It's unbelievably efficient, especially with big data sets. But my favorite feature, and this is a big one, is perfect data type preservation. You can say goodbye to your dates suddenly deciding they want to be strings. Plus, it's totally language agnostic, so it plays nicely with Python, R, Julia, you name it.
Okay. Talk is cheap, right? Let's see the proof. We're going to put these claims to the test with a direct head-to-head showdown. And trust me, this is where you're going to see just how much of a game changer this really is.
The setup is super simple. We've got a 1 GB data file. We saved it in 2 different ways. First, as a good old-fashioned CSV, and second, as a new school Feather file. Now we're just going to time how long it takes to read each one into our program. Simple as that.
And wow, here are the results. Reading that CSV file took a sluggish 45 seconds. Now look at Feather. 2 seconds. Just let that sink in for a moment. This isn't just a little bit better, it's a completely different world. We are talking over 20 times faster. That's the difference between grabbing that coffee and forgetting what you were even trying to do versus just staying in the zone and getting your work done.
Now, Feather is obviously a superstar, but it's important to know when it's the right tool for the job. Think of this chart as your cheat sheet. For pure speed and for temporary storage, like you're saving an intermediate step in your analysis, Feather is the undisputed king, no contest. But if you need to archive something for the long haul, and keeping the file size small is your top priority, then Parquet is probably a better choice. And as for Pickle and CSV, look, they still have their uses, but when it comes to performance, they're just not playing in the same league.
So right about now, you're probably thinking, okay, this sounds incredible, but it's got to be a huge pain to set up, right? Wrong. Absolutely wrong. Let's see just how ridiculously easy it is to get this working. I think you're going to be surprised.
Getting started is, and I mean this, literally this easy. You pop open your terminal, you type pip install pyarrow, you hit enter, and that's it. Seriously, there is no step 2. The whole Feather functionality is baked right in, and it'll automatically hook into the Pandas library if you've already got it installed. It's magic.
Now, let's see what this looks like in your code. You've done a bunch of work, you've got your beautiful Pandas data frame all ready to go, and you've called it df. To save it, you just write this one little line of code, df.toFeather, and then give your file a name. It's just as simple and intuitive as saving a CSV, but way, way faster.
And bringing that data back into your project, just as clean. The command probably looks pretty familiar. It's just pd.readFeather. And that's the real beauty of this whole thing. You don't have to learn some complex new system. You're just swapping out one tiny command for another in a workflow you already know and use. It's a tiny, tiny change for a massive, massive boost in performance.
I love this quote because it just perfectly nails what's going on under the hood. Reading a Feather file is like opening a box and finding fully assembled furniture instructions because the data is already stored in a ready-to-use format. But reading a CSV? That's like getting a flat pack from IKEA. You have to go through every single character, figure out where the columns start and end, and guess what kind of data is in each one. It's just so much more work for the computer.
So when you boil it all down, this isn't just some neat tech trick. It's a practical tool that gives you back the one resource you can never get more of, your time. So the only real question left to ask is, how much time are you going to save on your next project just by swapping out .2CSV with
Today, we're going to dive into a couple of techniques that can totally transform how you write code. We're talking about making your code more robust, way easier to maintain, and honestly, just a lot less frustrating to deal with.
I mean, you know the feeling, right? You're just staring at your screen, maybe pulling your hair out a little bit, chasing down some bug that feels like a ghost in the machine. It's got to be one of the most universal headaches for any developer.
And so often, after all that digging, the root of the problem is something that seems almost silly. You know, a function was expecting a number, but it got a string. Or you thought you were working with an object, but nope, it was none. It's these tiny little slips that end up causing the biggest headaches. So to really get why this stuff is so powerful, we kind of have to look back at this classic debate in programming, this constant tug of war between being super safe and rigid versus being creative and flexible. So on one side, you've got your static languages like Java or C++. They make you declare every single variable's type right at the start. It's great for catching errors early, for sure, but man, it can feel a little restrictive. Then on the other side, you've got dynamic languages like Python. They give you this incredible freedom and flexibility, but that freedom comes at a price, and that price is usually a nasty surprise error that only pops up when your code is already running. But what if you didn't have to choose? What if you could have it all? Well, that's where the industry has moved. It's this idea called gradual typing, where you can bring the safety of static types right into the flexible world of dynamic languages. You get that strictness exactly where you need it, and you keep the freedom everywhere else. And the way we do this is with our two heroes for today, type hinting and static analysis. You got to think of them as this powerhouse team that you can just add right into your workflow. So what even is type hinting? Well, think of it like adding little notes to your code that just spell out your intentions. The best analogy I've heard is that they're like guardrails on a highway, right? They don't drive the car for you, but they are incredibly good at stopping you from accidentally swerving off a cliff. And just look at this. The difference is night and day. On the left, who knows what name is supposed to be? We're just guessing. But on the right, it's crystal clear. This function takes a string and it gives you a string back. Boom. All the guesswork is just gone. Now for the other half of this amazing duo, static analysis. These are the tools that actually read your code and your type hints to find problems. This is your coding co-pilot. Seriously, it's running all the pre-flight checks to spot issues before you even try to run your program. And you really can't get the full effect without both. Type hints give the information, they lay out the rules, and the static analyzers are the referees that actually enforce those rules. It's this perfect partnership that makes them a real game changer. Okay, so we know what they are, but let's get to the important part. Why should you bother? Let's talk about the real-world benefits that are going to make your life as a developer so much better. We're talking about 4 huge wins here. First, your code becomes way easier to read for you and anyone else on your team. Second, your code editor suddenly gets a whole lot smarter, giving you amazing autocomplete. Third, you start squashing bugs before they even have a chance to exist. And fourth, your documentation is basically baked right into the code, so it never gets outdated. Let's just focus on readability for a second. That before function is a complete mystery box. What is data? A list? A string? Who knows? Now imagine you're new to a project and you see that. But the after version? It tells you the whole story, instantly. This means less time trying to figure out what code does and more time actually building cool stuff. And this is the magic right here. This is that safety net in action. You make a mistake, we all do, like passing the wrong kind of data to a function. But before you even hit the run button, that copilot, your static analyzer, taps you on the shoulder and says, hey, you might want to check this out. It's incredible. You know, a great way to think about it is that it's just like a spell checker in a Word document. It's not going to write your brilliant essay for you, but it's absolutely going to stop you from making simple, embarrassing mistakes. That's all these tools do. Okay, I know what you're thinking. This is the #1 question people have, and it's a totally fair one. We're adding all this extra info to our code. Surely there's a performance hit, right? And the answer, at least for a language like Python, is a big, loud no. Seriously. Type hints are for you, the developer, and for your tools. When the code actually runs, the Python interpreter just ignores them completely. You get all of these amazing safety benefits with literally 0 runtime cost. All right, so are you convinced? I hope so. The really good news is that getting started is way easier than you might think. You do not need to rewrite your entire codebase overnight. Let's look at how you can get going. Just about every major language has a whole ecosystem for this now. For Python, MyPy is the king. If you're in the JavaScript world, well, TypeScript has pretty much taken over. And even languages like PHP have amazing tools like SOM and PHP-stan ready to go. And here is your action plan. It's simple. Don't try to boil the ocean. Just pick one important file in your project. Add type hints just to the function definitions. That's where you get the most bang for your buck. Then run a tool like MyPy on just that one file. See how it feels. And I promise you, you'll want to expand it from there. You know, at the end of the day, this is really an investment. It's about changing your mindset from just make it work right now
to build something that will last, something that your future self or your future teammates can easily understand and build upon. By embracing type hints and static analysis, you're not just writing code anymore. You're engineering software. You're building that safety net that catches you when you fall and makes working with others a total breeze. So, the only real question left is, are you ready to start building more professional, predictable, and rock? In most software, a bug is, well, it's an inconvenience. But in finance, it can be an absolute catastrophe. Today, we're diving deep into the high-stakes world of testing for financial applications, where a single tiny mistake can cost millions. Let's break down how developers build the ultimate safety net. So let's just start with a question that honestly should give any developer a bit of a cold sweat. In a super complex financial application, what really happens when one small mistake, just one, slips through the cracks? The answer isn't some simple error message. The ripple effects can be absolutely monumental. And we are not talking about a minor glitch here. A single bug can trigger catastrophic failures. We're talking millions of dollars vanishing from accounts in an instant, regulators coming down with crushing penalties, and corporate reputations that took decades to build being shattered overnight. In this world, precision is completely non-negotiable. So how in the world do you build a safety net for something this critical? Well, it all starts with two fundamental types of testing. Think of it like this. First, you check every single individual part, and then you make sure the entire machine works together perfectly. First up, we've got unit testing. The best way to think about this is like building a skyscraper. You would never, ever start construction without making 100% sure that every single beam and every single bolt is flawless, right? Well, that's a unit test. In finance, this means verifying one specific function, like a compound interest calculation, to make sure it's perfect all by itself. And if unit testing is like checking the individual musician, then integration testing is the whole orchestra. This is where you verify that all the different parts of your system, the calculation engine, the database, that connection to an external API, are all playing together in perfect harmony. And here you can see them side by side. Unit testing is all about zooming in on individual functions to catch those little errors early. Integration testing, on the other hand, zooms out to look at how all the components work together to find any issues in their interactions. They aren't competing ideas. They're complementary layers of defense. Okay, so we get the principles. But what's the right tool for the job? Well, in the Python world, the answer for so many is PyTest. It's a framework that just perfectly combines power with simplicity. It's basically the ultimate Swiss Army knife for financial testing. So what makes PyTest so perfect for finance? Well, for starters, it has this incredibly clean, simple syntax. Your tests actually become so readable they can almost double as documentation, which, as you can imagine, is crucial for audits. But behind that simplicity is some serious power, with features that let you handle really complex financial scenarios with ease. At its heart, pretty much every test you'll ever write follows these three simple steps. First, you set the stage with your data. That's the setup. Second, you run the piece of code you're actually testing, the execute. And third, and this is the most important part, you assert that the result is exactly what you expected it to be. Setup, execute, assert. Simple. And here's what that looks like in practice. We're testing a compound interest function. You can see the setup in our inputs, the execution where we call the function, and then that final assert statement. But notice something interesting? We don't check for exact equality. In finance, you're often dealing with tiny decimal variations. So we check if the result is close enough to what we expect. It's a small detail, but it's incredibly important. All right, basic tests are great, but let's be real. Finance is rarely basic. So now we're going to look at how PyTest's more advanced features can handle the kind of complexity you see every day in real-world financial systems. Let's start with a feature called fixtures. Imagine you need to test a bunch of calculations on a sample stock portfolio. Are you really going to manually create that portfolio data for every single test? Of course not. A fixture lets you define it one time and then reuse it effortlessly across your entire test suite. It's a huge, huge time saver. And making one is super simple. You just write a function that returns your data, in this case our portfolio, and you pop that @pytest.fixtureDecorator right on top. Now, any test that needs this portfolio can just ask for it by name.
It's so clean and so reusable. Next up is parameterization. And oh man, this is a total game changer. Instead of writing a whole separate test for every possible scenario, you can write one test function and then just feed it multiple sets of inputs and expected outputs, just like you see in this table. PyTest will then automatically run that test for each and every row. This is how you test dozens of edge cases with minimal code. So what if your code needs to call an external service, like a live API for stock prices? You can't have your tests depending on that. It's slow, it's unreliable, and it might even cost you money. The solution is something called mocking. You basically create a controllable fake version of that API that gives you predictable results every single time, totally isolating your code for a pure test. But, having great tools is really just the start. Let's move on to the best practices that separate amateur testing from the professional-grade, audit-proof systems that are absolutely required in finance. This brings us to a key question. How much of your code should actually be tested? Now, it varies, but the financial industry often sets a pretty high bar, a minimum of 80% test coverage. And for the most critical parts, like the calculation and transaction engines, that number should be as close to 100% as you can possibly get. But here's a crucial warning, a pro tip, if you will. 100% coverage does not mean your code is bug-free. Not at all. It just means every line was executed by a test. The quality of your tests, how well they check for weird edge cases and flawed logic, that matters so much more than just hitting a number. And speaking of traps, here are two huge ones to avoid. First, over-mocking. If you mock too much, you end up testing a fake version of your system that doesn't even reflect reality. Second, ignoring test maintenance. Tests are living code. As your application changes, your tests have got to be updated right alongside it. The ultimate safety net, the final piece of the puzzle, is continuous integration, or CI. This is where you set up a system to run your entire test suite automatically every time a developer commits a change. If a single test fails, the change is blocked. Period. Nothing gets to production without passing the tests. It's your automated gatekeeper. Ultimately, everything we've talked about comes down to this one core idea, and this quote captures it perfectly. In finance, the cost of errors is measured not just in dollars, but in reputation and compliance. It's about trust, and it's about having the license to operate in a highly regulated industry. So, we'll end with this question for you to really think about. Whether you're building a massive trading algorithm or just a simple loan calculator, comprehensive testing isn't just a best practice, it's your insurance policy. So the real question is your code's safety net